And part 3 of section 10.7. This time we're going to reverse it. Now we're given a graph and we have to write an inequality for it. We see that it's a horizontal line and it's crossing the y-axis. So we know that it's going to be y. The line is dotted, so we know it's not going to be equal to. And I'm going to say that its y is greater than -1. And what we know, it's not going to be equal to because the line's dotted, and we can test. Let's test the point 0, 0. What would we expect to get? Well, it's shaded, so we would expect it to be true. So if we plug in 0, does it create a true statement? Yes. So I know that my equation is correct. So that would be the equation for that inequality, or for that graph. Here again, we have a vertical line this time. So I know that it's going to cross the x-axis. So x, and it crosses at 2. And this time, it's going to left, so that's less than. And I'm going to include the equal sign because I see my border line is solid. So that means those are solutions. So I want to include the border. I'm going to test that point. Is 0 less than or equal to 2? That's true. So my solution is this. And this is where it gets fun. So, a couple things. If we want to write an equation for the border, the first thing is, let's look at that y-intercept. It crosses the y-axis at 1, 2, 3, 4. So we know my y-intercept is going to equal 4. And let's take the slope. The slope, let's find another point. We go up 1, 2, 3, 4. And then we go right 3. So that gives me a slope of rise over run. We rise up 4, right 3, which converts to 4/3. So I know my equation is y 4/3 x plus 4. Now I got to think about this equation, right, or my inequality. Am I going to use, I see that it's equal to, so I know, is it going to be greater than or equal to, or is it going to be less than or equal to? Don't assume just because it's going, if we look at these shading, right, it shades up, so we go, oh, well, it has to be greater than or equal to. Well, we can also look at this. It actually goes -2. Oh, so that means it's less than or equal to. Well, the easiest way is to find a true value. So what is a true value? Well, this point's a true value. That's 1, 2, 3, 1, 2, 3. That's -3, 3. We are 100% confident that that is true. So let's plug those values in. 3 for y and 3 for x. So we get 3, and we don't know what this is going to be just yet. We're going to make it true. We know it's a true value, so we're going to have to make this statement true. We get 4 plus 4, 3, and 8. So what inequality sign would make that true? Well, a less than sign. So we know that our equation has to be less than or equal to. That would be our solution. Okay? We have to make this a true statement because when we plugged in the value is coming from the true side. So that's how you can do that problem. That's a fun one. All right, welcome to section 10.7, graphing linear inequalities. So linear equations, if we remember, a situation like y equals x plus 3, we would take that equation and we would use the y-intercept, 1, 2, 3, make a dot, and then we would use the slope. The slope is 1, so that's 1 over 1. We rise 1, run 1, rise 1, run 1. So we get 3 points, and that line would represent all of the solutions, meaning if we took this point right here, which is 2, 1, 2, 3, 4, 5, 2, 5, we plug it back into the equation, y equals 5, x equals 2, we would get 5 equals 5, meaning it's its solution. So that would be a true value. What if I pick the point 0, 0? If we plug 0 in for y, 0 in for x, we get 0 equals 3? No, that's a false value. And we know that any other point other than on this line would be a false statement, well, false point. That would give us, if we took that point, it would produce a false value, false value. However, anything on this line would produce a true value. And with equations, the line is the only boundary for contain only the true values. If I go to the right of it, I'm going to get a false. If I go to the left of it, I'm going to get a false. So it's a very small area. When we get inequalities, however, we are going to do the same thing. We're going to graph it in the same way, where we look at our y-intercept, which is 1. We're going to make a dot. We look at our slope, which is -1. So we're going to go down 1, right 1, down 1, right 1. And then we're going to draw a line. And that line represents some of the true values. And so what we need to understand is that from this point on, that line, in this case, because it's equal to, this is a very important understanding of when it's equal to, it's going to include the points on that line. Now, that line is going to separate true from false. So one side's going to be true, one side's going to be false. So if we test this point, let's take the point -5, 2. If we plug in 2 for y, -5 for x, we get 2 is greater than or equal to 5 plus 1, or 2 is greater than or equal to 6. Well, what do we know about that? That's a false statement. So this point on this side is false. And guess what? Every single point on this side is also going to be false. If one point is false, then all the points on that side of the boundary, of the line, will be false. Let's test another point. Let's test a point like 2, 2. So we plug 2 in. Y is equal to 2 minus, or the opposite of 2 plus 1. So we get 2 is greater than or equal to 1. And that's a true statement. So this point here is a solution. And guess what? Every point on this side is going to be a solution. So what we do is we shade the true side. We're always going to shade, because remember, these points represent true values. So what did we do with all these points? We shaded them by drawing a line. Well, now that it's an inequality, we're going to shade by doing these sort of long hairs, shall we say. So that boundary, that line, will separate false values from true values. When we have a single variable, we know that it's going to either be horizontal or vertical. So when it's one value, we know that x is going to cross, or the line's going to cross the x-axis at 1. Here's where it's 1, and we're going to draw a line. That is the graph of x is equal to 1, and now we have to test. And the easiest way to do this is test a point. If I test this point and I get, well, let's test it. So that point is 1, 2, 3, 4. 1, 2, 3, 4, 4. -4, 4. What's my x value? -4. Is -4 less than or equal to 1? That's a true value. So since I know that point is true, we know that this is the true side. So we're going to always shade the true side. So I'm going to draw those hairs. I don't have to test a point over here because I know that it's going to be false. So I really only need to test one point. We tested 2 here just to show that there was a difference. But from the point on, you don't have to test 2 points. You just have to test 1 point. So you test 1 point. If it's true, we know that that side is true. If it was false, we would know that the other side is true. So here's our equation. Again, we only have one variable. So we know that the line's going to cross the y-axis at 4. 1, 2, 3, 4. This time I'm going to use an open circle and dotted line. Can anybody tell me why that is? What's the one thing that's different this time? Notice it doesn't have an equal sign. So if I took that point right here, 0, 4, and I plug the 4 in, is 4 greater than 4? No, that would be a false value. Hence why it's open. It's an open circle. So this is still the boundary between true and false, but this time the boundary line is going to be false. This is the boundary line, and the boundary line is true because it's equal to it. So that's very important to understand, that when you have a greater than or less than, when you have greater than or less than, you're going to have dotted line and open circle for points. When you have greater than or equal to or less than or equal to, you're going to have a solid line and you're going to have a closed circle for your points because we want to include them. Don't include, include. Now we have to test a point. What's the easiest point to test? 0, 0. So let's test 0. Is 0 greater than 4? That is false. So we know this point is false, so we know the other side is going to be true, so we have to shade the true side. So we're going to shade the top side of that border. The next part is part 2. And part 2 is similar to part 1. We're just going to be given equations that are a little bit more complex or a little bit different. We notice in this example, we are not in slope-intercept form. So I'm going to rewrite it. I see that I have a less than or equal to, so I know that I'm going to include my border. My border is going to be true. So I'm going to go up 3, which is my y-intercept. My slope is down 1, right 1, down 1, right 1. I'm going to draw my line, and now I'm going to test a point. I'm going to test the point 0, 0. It's going to be my test. Is 0 less than or equal to negative 0 plus 3? Is 0 less than 3? That's true. So this point is true right here. So I know that every point on that side is true, and I'm always going to shade the true side. What we're going to do now is put some coordinates in here. We have 0, 3, we have 1, 2, and we have 2, 1. And that's sort of the most important part that I want to see are 3 points. You can write the equation on the line. I would love that. And then you're shading. Here's our next equation. So there's 2 things. We can either deal with it in standard form. Standard form, remember, helps us with the x and y intercepts. Or I can just subtract 2x from both sides, and I get y is greater than negative 2x minus 4. So we'll deal with it in this format, in slope-intercept form. Notice it is greater than, so I'm going to have to use open circles and dotted line for my border. So negative 4, 1, 2, 3, 4, open circle. My slope is down 2, right 1. Open circle, down 2, right 1, open circle. I'm going to use a dotted line to represent the border. I'm going to test the point 0, 0 is going to be my test point. So 0 for y, 0 for x. Is 0 greater than negative 4? That is true. So I know this point is true, so I'm going to shade the true side. Let's write the coordinates on here. That's 0, negative 4. That's 1, negative 6. And that's 2, negative 8. And y is greater than negative 2x minus 4.